Welcome to 4.4 Transformations with Matrices. Today we're going to use matrices to determine the coordinates of translated or dilated figures. We're going to use matrix multiplication to find the coordinates of a reflected or rotated figure. First, let's start with some vocab. So a vertex matrix, this is our matrix that talks about the vertices of our figures. The x coordinates are our top row, the y coordinates on the bottom row. Our columns create the vertices. A transformation maps points of a preimage onto an image. So the idea is it changes our picture, our figure. An isometry is a transformation where the preimage and image are congruent. So it does not change size or shape. Our types of transformations, a translation is a figure, it slides, so it does not change size, shape, or orientation. A dilation enlarges or reduces a figure. A reflection flips a figure over the line of symmetry, and rotation turns the figure around a point. So our first example is a translation. So the very first thing we have to do is to write the vertex matrix for the quadrilateral quad. So we have 2, 3, 5, 2, 4, -2, 1, -1. To translate the quadrilateral 4 units to the left, add -4 to each x coordinate. To translate the figure 2 units up, we're going to add 2 to each y coordinate. This can be done by adding the translation matrix where all of the x coordinates are -4 and all of the y coordinates are 2 to the vertex matrix of quad. Then we simplify and we get our new vertex matrix, q prime, u prime, a prime, d prime, where it's -2, 5, 1, 4, 0, 0, -3, 1. We're going to graph the preimage and the image. The two quadrilaterals have the same size and shape, so a translation is an isometry. The next example is a dilation. If the perimeter of a figure is 1/2 the original perimeter, then the lengths of the sides of the figure will be 1/2 the measure of the original lengths. We're going to multiply the vertex matrix, which is -2, -3, -5, 4, and 3, 2, by the scale factor of 1/2. Now we're going to multiply each element by 1/2, and we get -1, -3 halves, -5 halves 2, 3 halves 1. The coordinates of the vertex, so we're going to graph these two triangles. The triangles are not congruent. The image has has sides that are half the length of those of the original figure, so a dilation is not an isometry. Our next concept is a reflection. So for the reflection over the x-axis, we're going to multiply it by the vertex matrix 1, 0, 0, -1. We're going to do it on the left. For reflection over the y-axis, we're going to multiply by -1, 0, 0, 1. And for the line y equals x, we're going to multiply by 0, 1, 1, 0. So let's look at an example here. And the idea here is that we're going to write the ordered pairs of vertex matrix to start. So we have 1, 3, 3, 2, 3, -1, 1, -2, -1, 1. We're going to multiply on the left by the reflection matrix for the y-axis, which is -1, 0, 0, 1. Then we're going to use matrix multiplication, and we find the coordinate points are -1, 3, -3, 2, -3, -1, -1, -2, 1, 1. Notice that the preimage and image are congruent, so both figures have the same size and shape. So a reflection is an isometry. Our last concept here is how to rotate. We're talking about rotating counterclockwise about the origin. So if we rotate counterclockwise 90 degrees, we're going to multiply by the vertex matrix, of course on the left, by 0, 1, -1, 0. If we rotate 180 degrees about the origin, we're multiplying by the matrix -1, 0, 0, -1. And if we're rotating counterclockwise 270 degrees about the origin, we're going to multiply the vertex matrix by 0, -1, 1, 0. So let's look at an example here. First, we're going to write the ordered pairs in a vertex matrix. So we have 4, 3, 2, 1, 1, 5. Then we're going to multiply the vertex matrix by the rotation matrix. This is 90 degrees counterclockwise about the origin. So we're going to multiply on the left by 0, 1, -1, 0. We use matrix multiplication and we find the coordinate points to be -3, 4, -1, 2, -5, 1. If we graph this, we notice the image is congruent to the preimage, therefore rotations are isometries. Good luck on the practice.